All right, hello again. We are moving on to chapter 5, and in particular, I don't think you see this the way I'm uploading the book, but if you were reading the book as a whole, it's actually separated into 3 parts. And so there's part 1, which is the introduction, part 2, which is linear ODEs, and part 3, which is nonlinear ODEs. And we have graduated from part 1. Now we're in part 2. So chapter 5 starts part 2, and you can see very quickly why does it say linear ODEs when we start with linear operators here. So congratulations for making your way into part 2 of the book. We're going to start this chapter. This is actually a very short chapter. This is the only video on the chapter. We're starting the chapter with the definition of linear functions or maps. And you'll recall that from the linear algebra chapter, I know my code isn't finding that chapter for me right now, but for the linear algebra chapter, we made a point about linear functions versus affine functions, and I now represent the question: how should we define a linear function? And I really hope that you don't answer that f of x equals mx plus b is a linear function. F of x equals mx plus b is an affine function, and if we want to talk about linear functions, we have to choose f of x equals mx, and we have to get rid of b. We'll say why it is now. And it's because linear functions are the functions which, quote, look like multiplication, is what I think in my head. So if the function just looks like multiplication by m, that's what we define as a linear function. And we can make it a little bit more formal with the following definition. So a linear function or map over a vector space necessarily satisfies the following properties: that the linear map over the vectors au plus bv, where a and b are scalars and u and v are vectors, necessarily must distribute, and it must commute. So I'll say that right here. It must distribute, L must distribute, L must commute with scalars. So that's the 2 properties that L needs to satisfy to be called a linear function or a linear map on a vector space. And that's what I mean by behaves like multiplication, is because this is like the very natural idea that we have for multiplication, is distribution and commuting. So let's see why f of x equals mx plus b is not linear. Well, let's just compute f of a x1 plus a2 x2. If I compute that, I plug those in for x, and I distribute m, and I could definitely distribute and commute m, but nothing is happening when it comes to b with regards to distributing or commuting. So now, because if I compare what I would want this to be equal to, so in linear I take f on the outside has to be the f on the insides separated. If I take f on the inside separated by the plus signs, you'll notice I recover an a1 plus a2b. Well, if a1 and a2 don't add up to give me 1, then that's never going to be true. So this function cannot be linear. And I have a footnote to describe some more things for you if you still don't feel good about that. But we move on to the next example, which says, okay, in the specific case when b is 0, then it is linear. So in the specific case when b is 0, then my function is linear. And this is what I mean to say when I say it looks like multiplication. If we move up our dimension, right, this was in 1 dimension. F took one-dimensional vector space of the real numbers, and it maps that space to itself. If I jump up a dimension, or maybe to multiple dimensions, to d dimensions, our linear maps are precisely the matrices. Okay, so f of x equals m, a matrix times x, is a linear map in higher dimensions. And in fact, this is why it's called linear algebra. Right. Okay, we have a little bit of interesting notation, vocabulary, perspective on linear maps that I want to mention here. And that's that rather than writing that the functions, which are the maps, are linear, we use this abusive language, and we often just say like m, which is interpreted as multiplication by m, or capital M interpreted as multiplication by the matrix m. So like matrix multiplication, scalar multiplication, we consider those linear maps, but we'll just like say that the object itself is linear, even though we're supposed to interpret it as the map, which the object induces, is actually what's linear. So that's just some vocabulary we use, and because of that, now I can present the following, which is useful. If I take derivatives d dz, I guess, of an analytic function or something, a derivative is a linear map, right? So this considered as a map on functions is a linear map. How do I know that? Well, I can compute the derivative on af plus bg, and we all know that that's equal to af prime plus bg prime, which is the same thing as computing the derivative individually on f and g and then putting them into the linear combination. Similarly, antiderivatives or integrals are linear. We want to get used to thinking of integrals like this as antiderivatives. Maybe I'll describe that over here now. This is and I say it's not it's an antiderivative of f. And maybe to be particularly correct, I should get rid of that variable and put a new variable inside. That's why I was using the zeta earlier. So if I integrate a function and I leave my upper bound of integration as a variable, right? I'm calling this a function of the upper integration bound. So that function of the upper integration bound is an antiderivative. And so we're going to get used to using that notation to describe antiderivatives instead of the indefinite integral, which is just slightly more vague than this one, which like fixes an antiderivative for us. We don't need to worry about plus c in these cases. So no need to worry about plus c for these cases, which is kind of why they're useful. We just kind of forget about plus c and we just say this is an antiderivative. Well, anyway, that was a bit of an aside. That's a linear map because we can compute the antiderivative, and we know that the antiderivative computes on each f of z and g of z separately, and then we recombine them together. So those are linear maps. And in fact, the linear algebra is the concatenation, also considered as a composition of maps, right? If I take one map and then compose it with another map of any number of linear maps is a linear map. Okay, so what I mean by that is just like L1, L2, both linear, are together linear. Okay, we don't all of a sudden push ourselves away from being linear just by doing one map and then the other. We always stay linear as long as everything else is linear, which is useful. That's what gives us the linear algebra. So here's the remark. So an algebra is a vector space which has a well-defined multiplication of vectors, and it turns out that the space of all linear maps from a vector space to itself is actually itself a vector space. We can form a vector space of matrices. And so under this composition, that's where you gain what we call the linear algebra. So by this interpretation, the course that you've probably taken, which was called linear algebra, should be given the name, what a mouthful, the algebra of linear maps on finite dimensional vector spaces. That's really what the course title linear algebra means, is they took linear right here and algebra right there. And in fact, your linear algebra is the algebra of linear maps on finite dimensional vector spaces, right? The finite dimension is very important there because if we move to infinite dimensions, this is the course that you've often heard of or perhaps heard of called functional analysis. So really, functional analysis can be translated as the algebra and analysis, because we will have to use analysis in such a course. So it's the algebra and analysis of linear maps on infinite dimensional vector spaces. So these two topics of linear algebra and functional analysis are basically, you can start with linear algebra. That's what you're doing as an undergraduate. You start in C, D, or perhaps R, D, right? And as you take D to infinity, you kind of recover this idea of functional analysis. And you have to be careful about where is the analysis coming from. Well, analysis is basically the mathematical study of infinite objects, right? That's one way you can think about mathematical analysis, is the study of infinite objects. So that's really why we transition from linear algebra to functional analysis. But there's a lot of like overlap in like the notions that are involved. So like spectrum are very important, eigenvectors, eigenvalues, linear maps, and so on are very, very important in both linear algebra and functional analysis. But we're dealing with different dimensions of spaces. Okay, some good footnotes for you there. Now we're going to move on to section 2. This is thankfully a little bit shorter of a chapter today. And we're going to move to linear operators. So I guess once again, I want to mention that we're moving with t being temporal and x being spatial input. Don't know why I included that in there. All right, so a linear operator is a linear function from a vector space to itself, but for my purposes, I'm going to require that V is a function space. then I'm going to let L be a linear operator. So we have these matrices on finite dimensional spaces, which I would argue most of the time aren't function spaces. And then once we push ourselves to infinite dimensional spaces, that's when I like to say we're dealing with linear operators. So for example, derivatives are linear operators because not only are they linear maps, but they act on functions, right? So we've already computed that they're linear maps, and now we recognize that, yes, they act on functions, and that's what makes them linear operators. And then the same thing with our antiderivatives, okay? So this is how your antiderivatives would look in the x and t variables. Those are both linear operators as well. Finally, I want to cover this next one, which will be important for us, and this is called the multiplication operator. This is specifically the operator which is going to act on a function space, and it's going to multiply that function by a new function, which will be the subscript. So just because we use a capital M, don't think this is a matrix. It is an operator. The subscript f should help you remember that. So M sub f as an operator acting on the function g is defined to just be the function f times the function g. And in fact, that will be a linear operator, right? All right, so this theorem is probably the only important piece of this chapter, and that's the representation of a linear operator. When I say representation, there's actually an entire field of math called representation theory, and that's kind of what we're invoking here. Representation theory is the act of taking a mathematical object and representing it by a matrix, or representing it technically by a linear map on a vector space. But what we're going to be doing is we're going to be taking a new perspective on a linear operator, right? This could be any linear operator, and we're going to actually give it the perspective of an infinite matrix. We will give L the representation of an infinite matrix. Okay, so that's what this theorem is all about, is somehow can I reinterpret a linear operator L, which acts maybe on an infinite dimensional space, as an infinite sized matrix. So if I scroll down a little bit, what I'm going to do is start with a vector space, and this is why we encountered the vector spaces we did in the last chapter. So I'm going to start with a vector space with a basis, orthonormal basis, E sub n, and then without loss of generality, I can let that be little L2. Okay, so I have my orthonormal basis in my vector space, and I'm going to define, this is a number. I'm going to define a number, a complex number, L sub nm. So that's a complex number, and it gets defined by computing an inner product of L on some of the elements of my orthonormal basis against another element of the orthonormal basis. So I'm computing an inner product of the linear operator on one element of my orthonormal basis, and then against another element of the orthonormal basis. And because inner products output complex numbers, then I just get this nice sequence. It's a sequence of complex numbers in the kind of like in the indices n and m, right? So the indices are n and m, and I've produced a sequence of those. So for any function in my vector space, I can compute the, first of all, I can write the function as an element of the vector space using the orthonormal basis property, where it's just equal to an infinite sum against the orthonormal basis. But if I want to, I can compute L on that function. Suppose I didn't really know how to compute L on the function in the first place. As long as I compute all of these nice inner products against the orthonormal basis, all I do is now compute L sub nm against the coefficients of f, which were a. So I compute those against a sub m, they've been indexed by m here, and I sum all of those up. Now for each fixed n, I sum all of those up, and I put that number, I'll say that here, this, after the sum, is a complex number dependent on n. So I have a complex number dependent on n, so I really have a sequence of complex numbers that gives me, if I sum over n now, call those complex numbers bn, that gives me my new element of v. Okay, and I know this is very confusing. It's going to be much more concrete when we look at some examples of this. But all I'm trying to say is, in fact, if we look at this right here, this term right here, this looks exactly like matrix multiplication of the matrix capital L, where the nth row, nth column is given by this number, And then A sub m is the vector which the matrix acts on. So this is actually precisely matrix multiplication of L against F considered as a vector. So we're going to scroll down a little bit. There's the proof there. That's really not that important. But if we look down, here's really what I was trying to reference, is I'm saying that we can reinterpret a function just as its sequence of coefficients, right? So let's say f as a function, maybe it's equal to the Taylor series, right? This is a sub n x to the n. It's equal to its Taylor series, but let's forget about x to the n for now and just consider the a sub n's as a nice sequence and represent that sequence like a vector. And if we do that, if we represent that sequence like a vector and each of the en's as the identity vectors on those entries, then what we recover is that we can represent L. If L acts on F, then L could also act on the infinite vector as an infinite matrix. But the only question is, how do we actually calculate the entries of that infinite matrix? We have to calculate the entries of the infinite matrix as L M N is L E M E N. And I hope I got my order correct. I might have screwed up the order at the bottom. It's either that or the transpose, of course. You can verify above if the order is correct there. And so that's how I calculate each of these entries, is as an inner product with the basis elements. And once we do that, we consider L on F as an infinitely large matrix acting on an infinitely large vector, and we just compute the matrix elements. Just compute your standard matrix multiplication like we had in our linear algebra chapter. I consider this row dot product the vertical vector. I consider this row dot product the vertical vector. I consider this row dot product the vector. And that's what gives me each of these, right? I have that one from orange, I have this one from blue, and so on in purple. That's how we can consider linear operators as infinitely large matrices. Looking really quickly down to the next example, I'm actually jumping back down into finite dimensions because that's a little bit more tractable for us when it's our first time around, and I'm making the strange statement that a matrix is not a linear operator, or it's not a linear map, it's a representation of a linear map, okay? Because if I take a given linear map, this one that I've defined, if I'm taking this linear map, which I'm defining to take the vector x1, x2, x3 in, and output these numbers, there's nothing that's telling me that I need to define this as a matrix. It's perfectly well defined as it is, and yet if I wanted to represent it as a matrix, I could. Right, so they're not metaphysically the same object, but I could represent it as a matrix. And if I were to represent it as a matrix, I can calculate its representation as a matrix using the standard orthonormal basis, 1, 0, 0, 0, 1, 0, and 0, 0, 1, and I can find out that the entries of my matrix are precisely L11 is LE1 against E1 dot product, and if I compute those dot products, I get 3 for L11, I get -2 for L12, and if I continue all the way around, I get that every single L can be computed from the dot product of L against one orthonormal vector against, and then inner product with the other. And that's what's going to give me the matrix, which is only a representation of the linear operator. So taking these as a matrix gives me a matrix representation of a linear operator. And yet the linear operator doesn't have to be the matrix itself. Anyway, there's my matrix. Final example is a pretty cool one. If I decide to run through this matrix representation of the derivative as it corresponds to the Fourier space or the Fourier series, so if I consider a derivative on a Fourier series and try to compute like the entries of the infinite matrix that would be, I actually get precisely a diagonal matrix. Okay, so notice here the only non-zero entries are inside of the diagonal of this matrix. Everywhere else is a 0. And so the Fourier series actually is in some sense, the basis choice, e to the I n 2 pi over theta 1 minus theta 0, theta over n is that's this capital X for which x inverse derivative x, maybe I'll call that so I don't get confused, d theta X is a diagonal matrix. Right? This is precisely matrix diagonalization in infinite dimensions. I've made a choice of basis, or I've found infinitely many eigen vectors, right? These are all eigenvectors, and I've found infinitely many of those. I placed them into this matrix, capital matrix X, and all of a sudden I recovered a diagonal matrix. So that's really what's going on with the Fourier series, and that's why it's so important for us, is that this is like matrix diagonalization in infinite dimensions. And so we gain all of the beautiful properties that arise from working with diagonal matrices, specifically for derivatives. And hey, what do you know? We're in differential equations where the derivative is kind of the most important object. So that's why the Fourier series is so darn important for us. Anyway, that's all I have. Thanks for sticking with me. I'll see you in class.